Welcome to this explainer. I am absolutely thrilled you're tuning in today. We are going to be unlocking the incredible under-the-hood mechanics of algebra by exploring linear equations. I really want you to think of math not as some rigid, boring set of rules, but as this incredibly elegant system of balance. It's basically a way of discovering hidden truths, just one step at a time. Okay, let's dive into this.
Here is our roadmap for today. We're going to start with one-variable equations, and then figure out how to actually solve for the unknown. After that, we'll introduce a second variable, explore simultaneous equations, and finally, we'll tie the whole shebang together with the golden rule of balance.
Section 1. One-variable linear equations, the foundation of algebra. I really like to think of every math problem as a bit of a mystery, where variables are simply these hidden identities just waiting to be uncovered. So, let's look at the foundational rules for solving these mysteries. Let's look at the strict definition here. A linear equation in one variable contains exactly what it sounds like, just one unknown letter, like an x or a y. But here is the absolute most important rule. The power of that variable must be exactly 1. So no squares, no cubes, just a single plain variable. And if you were to graph it, it would form a perfectly straight line.
And this brilliantly illustrates that rule in action. On the top, 3x plus 2 equals 5 is a perfect example. There is just one x and its power is 1, so that gets a big yes. But look right below that, y squared plus 3y equals 1. Even though there's only one type of letter being used here, that little squared symbol completely breaks our golden rule. The highest power is 2, so it is categorically not a linear equation.
Section 2. Solving for the unknown, finding the elusive x. So now that we can easily spot a linear equation in the wild, it's time to learn how to force the equation to reveal its secrets to us. Let's move from abstract theory and step into the real world for a second.
Here is a super relatable, everyday scenario, drawn straight from a typical Malaysian shopping trip. Imagine Lily goes to the store. She grabs 5 pens, but we don't actually know the exact price of those pens yet, so we'll say they cost Y-sen each. She also grabs an exercise book with a very clear price tag of RM3. At the register, her grand total comes out to RM7.
To solve this, we just need to translate Lily's shopping trip into the language of math. Now, because her pens are in cents or cent, we definitely need our units to match up, so that RM3 becomes 300 cent and the RM7 total becomes 700 cents. Our equation now perfectly models reality. 5 times the unknown pen price plus 300 equals 700. And just like that, boom, we have our one-variable linear equation.
Now, how do we actually solve these things? Let's look at a new equation for a moment. 2x plus 1 equals 7. The most intuitive method is called trial and improvement. Honestly, we just guess. If we try an x value of 1, the result is 3. Well, that's way below 7. If we try 2, the result is 5. Still too low. But when we test 3, 2 times 3 is 6, plus 1 is 7. Perfect. The balance is struck.
While guessing totally works for simple problems, the equality concept is your true mathematical superpower. So, the crucial point is this: whatever you do to one side of the scale, you absolutely must do to the exact other side to maintain perfect equality. To isolate x in our equation, 2x plus 1 equals 7, we first subtract 1 from both sides. That easily gives us 2x equals 6. Then, we divide both sides by 2. The result? X equals 3.
Now, a third really fantastic strategy is the backtracking method. I like to think of this as rewinding a movie. You literally start at the end, the final value of 7, and then you just reverse every single mathematical operation. Instead of adding 1, you subtract 1, which gives you 6. Instead of multiplying by 2, you divide by 2, and that brings you right back to your starting value of 3. 3 completely different methods, but one undeniable truth.
Section 3. Introducing a second variable, expanding dimensions. Okay, so we've completely mastered a single dimension. Let's move on and see how this builds when we add an entirely new layer of complexity to our equations.
Welcome to the vast world of two variables. The standard form here is ax plus by equals c. Notice that we now have two distinct unknown identities, an x and a y. But crucially, our golden rule hasn't changed one bit. To remain a linear equation, the power of both variables must absolutely remain exactly 1.
But here is the truly mind-blowing shift. When we had one variable, there was only one specific answer, like x equals 3. But the very second you introduce a second variable, the answer is no longer a single point. It becomes this endless relationship. These equations possess many possible pairs of solutions, which, if you plotted them out, physically form a straight line that stretches infinitely on a graph.
Let's actually test this out with the equation 2x plus y equals 6. If we just decide x is 0, well, then y has to be 6 to balance the equation. But if x steps up to 1, y dynamically adjusts down to 4 to keep that perfect balance of 6. If x is 2, y is 2. Every single time you change one variable, the other one dances along to compensate. It's literally infinite pairs of solutions.
Section 4. Solving simultaneous equations where lines meet. So, what on earth happens when we take two of these infinitely long, straight lines and place them in the exact same universe?
Well, when you have a pair of linear equations that happen to share the same two variables, like an x and a y, you have what we call simultaneous linear equations. We are no longer just looking for any random pair of numbers that balances one equation. No, now we are hunting for the exact specific pair of numbers that makes both equations perfectly true at the exact same time.
When two lines exist in the very same space, they really only have three possible destinies. Number one is a unique solution, meaning the lines cross at exactly one precise intersection point. Number two is no solution at all. This means the lines are completely parallel and they're just going to stretch to infinity without ever touching. Or number three is infinite solutions. This happens when the lines overlap so perfectly that they are actually literally the exact same line.
Now, what's really interesting to see here is how beautifully visual this can be using the graphical method. If we take our first equation, x plus y equals 6, and our second equation, 2x plus y equals 8, and we simply draw them out, their literal intersection point on the graph is our answer. They cross perfectly at x equals 2 and y equals 4. That right there is the one and only common truth they share.
Now, if drawing graphs isn't really your style, we have some clever math tricks up our sleeve. The substitution method is basically a brilliant disguise. You take equation 1 and rearrange it so x is entirely by itself on one side. X equals 7 plus 3y. Now, whenever you see an x in the second equation, you just substitute in that whole disguise, 7 plus 3y. Suddenly, the x entirely vanishes. You've successfully collapsed it back down into a simple one-variable equation, allowing you to easily solve for y, which is -2, and then you just plug that back in to find out that x is 1.
Then, of course, we have the real powerhouse approach, the elimination method. Notice how in these two equations we have a positive 2y and a negative 2y? If we simply stack these equations up like an old-school addition problem and just squash them together, the 2y and negative 2y literally cancel each other out completely. They are eliminated. We are left with just 4x equals 24, meaning x is 6. Substitute that 6 right back into the original equation, and y emerges as 3 over 2. It's fast, it's clean, and it's highly efficient.
Section 5. The Golden Rule of Balance. Summary and takeaways. All right, let's bring all these incredible building blocks together under one unified theory of algebra.
Here are your definitive keys to mastering all of this. First, maintain equality. It's a scale, right? What happens to the left absolutely must happen to the right. Second, know the power. Remember, linear is a very strict club where variables can only ever have a power of exactly 1. And third, always double check. This is huge. Once you find your answers, you hold the ultimate power to prove yourself right by simply substituting your values back into the original equation to see if it balances out. Think about how profoundly elegant this whole system really is. It literally brings order and reason to the unknown. Which actually leaves me with a pretty interesting question for you to ponder today. If mathematical equality requires absolute, perfect balance on both sides of the equation, how can you apply this identical golden rule of balance to analyze and solve the complex, multivariable problems in your own life outside of the classroom? Thanks so much for learning with me in this explainer today. Keep seeking that perfect balance.